So before I start, I just need to give a plug to Xenon Systems. So who is Xenon Systems? Xenon Systems is an Australian-based systems integrator and reseller. We're headquartered in Melbourne, founded in 1996. Now Xenon is probably one of the most, or if not the most experienced, largest HPC team in Asia-Pac. When I started around about 9 years ago, a bit less than 9 years ago, there were 12 people at Xenon. Now there's about 40 people. And most of those staff that have been added have been technical staff. Initially, we were operating across Australia. Now we've expanded staff. We're expanding our services and our scope across the Asia-Pac region. Our core focus is in HPC research and serving the scientific and technical user community. The services that we offer, or the solutions that we offer, include compute storage, networking solutions, as well as tailored services around those type of solutions. So deployment solutions, installation, ongoing managed services, etc. Our user base mainly is made up of universities, research organisations and government agencies. One of the advantages, I suppose, with Xenon Systems is that we're hardware, software and solution agnostic. When we offer solutions or when we offer proposals to customers, sometimes we'll include competing options in our proposals for the same requirements. So we give a lot more choices, or we think we give a lot more choices to customers when they come to us for a solution. And we pride ourselves on delivering first-class, innovative, price-competitive solutions. As I mentioned, we're expanding into the Asia-Pac region. We've already supplied and deployed solutions here in New Zealand, and some of the customers include NeSI, Todd Energy. We've just deployed the Versity solution that was talked about for both NeSI and NeSI. So my talk's about quantum simulation, and it's the work that's being done by PAWSI. So let me just introduce PAWSI. So PAWSI is a supercomputing centre based in Perth, Western Australia. It's one of 2 Tier 1 HPC facilities in Australia. The other one is NeSI, that's based in Canberra. It is funded by both the Western Australian state government and the Australian federal government. It's home to the most powerful research computer in the Southern Hemisphere, and that's a great big Cray system of around about 1,800 nodes. It's also the home of some pretty big storage repositories. And the 2 big ones they've got over there are Acacia and Banksia. So Acacia is a 90+ petabyte Ceph object storage cluster. We were lucky enough to be awarded to expand that by 30 petabytes. So about 18 months ago, it was 60 petabytes, and we were asked to expand that by another 30 petabytes, so now it's 90 petabytes. And Banksia, so Banksia is their archive storage tier, similar to probably NeSI's Freezer. It's based on Versity Scout AM. It's 130 or 140 plus petabyte archive storage. It's got 2 big Spectra T-Infinity tape libraries that manage around about 70 petabytes each. And that was designed, supplied, deployed and supported by Xenon Systems. PAWSI is also the home of the world's first room temperature quantum computer at a HPC facility anywhere in the world. And they've done this with their partnership with Quantum Brilliance. And it's also host to Australia's first race hopper-based HPC system. It's a small cluster system. And Xenon supplied that along with 0.5 petabyte of Weka storage. And the primary use of that is for quantum simulations. Just to continue on to explain very quickly what PAWSI do. So PAWSI supports around about 4,000 researchers. It provides large-scale, high-speed computational and data resources, a whole bunch of advanced software tools for researchers to use. And the researchers use these resources to tackle the problems in their specialised domain, and it covers astronomy, climate science, bioscience, engineering, and energy and resources. It's managed by around about 50 staff who are employed by CSIRO. CSIRO is Australia's national scientific agency. So you're probably wondering, why would you simulate quantum computing on classical hardware and not just run it on quantum computers? Well, today quantum hardware has limitations. It's got limited qubits, tens of hundreds, and that restricts their viability, restricts the problem size, the complexity that they can run. Also, quantum computers these days are highly sensitive to noise, prone to error. So very easy, they are today are very unstable to use. So running quantum simulations on classical hardware allows us to run or explore quantum systems without these hardware limitations. It provides a practical step for advancing quantum computing and its understanding. It allows us to develop software to enable design, refinement and debugging of quantum algorithms. Classical simulations also make it easier to debug these algorithms because running simulations on classical hardware provides deterministic results, understandable computational pipelines. It also allows us to prepare for the future. So we're developing and refining these quantum algorithms. So when quantum computers become more viable in the future, become more stable, we're in a better state to start using those. Also, running quantum simulations on classical hardware provides further insights into the key principles of quantum mechanics and quantum computing, phenomena like superposition, entanglement and interference. And it also provides the opportunity to allow us to explore and highlight the problems where quantum computers can outperform classical computers. So it gives us the opportunity to work out what would really work well when quantum computers become more available, more feasible, more viable. Obviously, optimisation, cryptography are two main areas where quantum computing do very well. So as I mentioned in the intro, PAWSI leverages a small Grace Hopper HPC cluster with Weka storage for these quantum simulations, and they call this little cluster Ella. Most of the quantum simulation code was initially developed on x86 hardware, and PAWSI have been migrating that across to the ARM-based Grace CPU Although the porting had some challenges, Pawsey tell me it wasn't too painful. So they've done the porting of the code across to the Grace Hopper platform, and they found it reasonably straightforward. So why would you use the Grace Hopper? What makes that interesting? Well, for Pawsey, the Grace Hopper superchip architecture, that is the Grace CPU and the Hopper GPU architecture, offers a unified memory. Pawsey is exploring how they can streamline their quantum simulations to take advantage of this superchip's unified memory architecture. So what it allows the GPU and the CPU to actually share the same shared memory pool. So in traditional computers, normally you have to move the data between the CPU and the GPU. But because the GPU and the CPU in this architecture sees the same shared memory pool, they don't need to be moving data in and out between those two to those nodes. The CPU and the GPU threads can access the same memory pool, no need to move data. And this is done with the NVIDIA NVLink, which provides a memory coherency between the CPU and the GPU. And as far as the operating system is concerned, it sees the CPU and the GPU as just separate NUMA nodes. So Pawsey is tackling hybrid workflows combining CPUs, GPUs and QPUs, QPUs being quantum processing units. And they use virtual QPUs to mimic real-life quantum hardware by introducing noise alongside developing orchestration tools and testing systems integration. Also, Pawsey are developing tools for scalable quantum simulations addressing the inefficiencies in the current GPU usage and scaling limitations of existing packages, concentrating on optimising problems in areas such as chemistry applications, quantum machine learning techniques. The progress highlights so far, they've advanced several research projects. They haven't released the outcomes of those projects yet, but the details of those will be forthcoming. They've been doing benchmark simulation on different frameworks. They mainly use the Q2Q. They're exploring and, as I mentioned, they're exploring and reviewing different frameworks, trying to work out what works well and what doesn't work well. They're also creating a lot of in-house efficient quantum computing simulation codes specifically optimised for the Grace Hopper superchip architecture. So Pawsey have also employed 3 interns who are actively testing the system and exploring the scaling of quantum simulations that can be feasible. They are, as I mentioned, they are using a number of frameworks and doing benchmarking in ways that would be fairly challenging if they didn't have Ella and the superchip architecture. Pawsey are also developing in-house quantum simulation codes, which I mentioned. Ella serves as an excellent test bed to evaluate their scalability. And Pawsey has stated that Ella has been a highly valuable as a non-production system for their team of experienced early adopters. So just in summary, Pawsey quantum computing research, including the quantum simulations done on the Ella system, has been progressing well. Pawsey exploring how quantum simulations can leverage the unified memory architecture of the NVIDIA Grace Hopper superchip PAWSI are developing and testing quantum computing algorithms and tools, identifying what works well and what doesn't work as well. The team have actively engaged in several quantum computing-based research projects. PAWSI's view of the quantum simulation project is that they see this as a practical and essential first step in understanding quantum simulations. A lot of the information I got from this talk, I've got from Dr. Pascal Alahi. Pascal is a HPC and quantum specialist at PAWSI, so I'd like to thank him and acknowledge his work in the work they're doing over there. Thank you.
What kind of problem are they focusing on in terms of simulating?
What sort of problems?
Yes.
Well, at the moment they're doing a lot of working on a lot of codes tools for quantum simulation, but they're also doing a lot of codes around optimisation. They have a number of research projects going on at the moment. I don't know the details of those. They haven't given me the results of those at the moment, but they tell me the results of those are going to be published fairly soon. The other thing I should probably be, I forgot to mention is there's also a lot of information out on the web. So the NVIDIA CUDA-Q is the framework that they use, and there's also web pages on the work that PAWSI have been doing with the quantum simulations. So I would recommend people to have a look at those web pages as well. Thank you.